Good day, everyone. We are still on the tangent secant power theorem, but this time we will take a look at examples on the applications of this tangent secant power theorem. Our task, therefore, is to apply the tangent secant power theorem in determining measures of segments or values of variables. Just a quick recall that the tangent secant power theorem states that if a tangent and a secant intersect in the exterior of a circle, then the square of the measure of the tangent is equal to the product of the measures of the secant and its external secant segment. By the figure, and we can say that the square of the tangent segment, which is DE, so we square that, is equal to the measure of the segment secant, that is BE, multiplied by the outer part of the secant, and that is segment CE. That is what we're going to apply. Example number 1. We have here a figure, and of course we have a tangent and a secant intersecting outside the circle, and we are tasked to solve for x. So what would be the very first thing for us to do? Always set up the equation based on the tangent secant power theorem. That is x squared, x being the tangent segment, is equal to 9, which is the outer segment of the secant segment, multiplied by the whole secant segment, which is now the sum of the measures 9 and 16. Then, after setting up the equation following the tangent secant theorem, power theorem, we are now ready again to simplify. Thus, we have x squared is equal to, adding 9 and 16, we get a 25. Furthermore, you have x squared is equal to 9 times 25, giving us 225. Inasmuch as we have a square, we undo squaring by taking the square roots of both sides of the equation. Thus, we will be arriving at the square root of x squared is equal to a positive and a negative square root of 225. So there are actually two values that are possible. One, we get x is equal to the negative square root of 225 being negative 15. But remember that we are talking about measures. Thus, this is an extraneous solution as x must be positive. The other value, x is equal to 15, which is the actual value for x, inasmuch as it is the value that is positive. Our example number 1. Let's have another example. Still, there is a secant, there is a tangent, and we are tasked again to solve for x. Setting up the equation, we have 8 squared, 8 being the measure of the tangent. So we square that is equal to x, which is the measure of the outer part of the secant segment, and multiply that with the whole secant segment, which now measures x plus 12. Simplifying, performing operations, we have 8 squared is 64. Then we have x times x, we get an x squared. And then we have x times 12, we get a 12x. Inasmuch as the highest exponent is 2, giving us a quadratic equation, we transfer every term to one side of the equation, giving us 0 is equal to x squared plus 12x minus 64, as we undid the plus 64, or we transferred 64 from the left side of the equation to the right side, thereby changing its sign. Then we solve the quadratic equation. Is it factorable? Is the trinomial factorable? Yes, it is. So factoring, we will now be having 64, negative 64, having the factors 16 and negative 4. So if we're going to check, 16 times x is 16x, and x times negative 4 is a negative 4x. So if we add that, we will arrive at the correct middle term. Then again, we apply the zero property, wherein if we are given a multiplied by b is equal to 0, then a must be equal to 0 or b must be equal to 0. So we take one of the factors. We have x plus 16, and we equate that to 0. So transferring our 16 to the other side, we come up with x is equal to negative 16. Again, the value is negative, so this is still an extraneous root, as x must be positive in as much as we are dealing with measures. The other factor, x minus 4, we equate that also to 0, giving us x is equal to 4, which is the actual value of the x. So therefore, we were able to answer the given wherein we were tasked to solve for x. Example number 2. Let's proceed to example number 3. Still, we are given a circle with a secant segment and a tangent segment intersecting outside the circle, and the point of intersection is point M. Again, we set up the equation. What would be the equation? Let's identify the tangent, and the tangent segment is MN. Therefore, we square its measure, and we equate that with ML. ML is the outer part of the secant segment, while MK, not LK, but rather it's not an L, it's an M. Okay, ML times MK, that is the whole secant. So we substitute values. We have the tangent segment has a measure of the sum of x and 3. So we square that. Then we have the outer part of the secant segment, which is the x plus 3, marked in the figure with red for us to be guided. And the whole secant, which is mk, not lk. We are now adding x minus 3 plus 16. That's the measure of the whole secant segment. We simplify by performing the indicated operations in this equation. So thus we have, when we square x plus 3, we arrive at x squared plus 6x, that is x times 3 times 2, plus the square of 3, which is 9. Then we simplify also negative 3 plus 16, giving us a positive 13. Further simplifying by multiplying the two binomials at the right, you have x times x is an x squared. Then you have a negative 3x and a positive 13x, giving us the sum of a positive 10x. Then we multiply negative 3 and 13. We have a negative 39. Again, we have squares on both sides of the equation. Let's put together all the terms on one side. Thus, since we transferred x squared from the left side to the right side, it became negative x squared. Positive 6x to the right side, it becomes negative 6x. And positive 9 to the other side gives us a negative 9. Performing again operations, we are left with 0 is equal to 4x minus 48. X squared plus a negative x squared will give us a 0. Then we have 10x positive and a negative 6x, will give us a positive 4x. Then, a negative 39 plus a negative 9 gives us a negative 48, leaving us with a linear equation. Thus, we transfer negative 48 to the other side. 48 now is equal to 4x. And undoing the operation 4 times x, we divide both sides by 4 and we arrive at the value of x to be 12. And thus, we were able to answer what is the value for x. That's example number 3. Let's proceed to the final example for this video. We are given the tangent ER intersects secant PR at R, that is outside the circle. Determine the length of RQ and QP. Let us see. We set up the equation. We have the measure of the tangent, that's ER, we square that, is equal to RQ. RQ is the segment, part of the secant outside the circle, and we have here multiplied it by PR, which is the whole secant segment. We do substitute the values. ER has a value of 12 as given, and we square that. RQ, we do not know the value of RQ, so we say let X be the value of RQ. Then we have the measure of the whole secant segment is given to be 18, that's PR. So we proceed to perform the operations that are indicated. 12 squared will give us 144, and 18 times x will give us an 18x. Undoing 18 times x, we divide both sides by the equation by 18. So 144 divided by 18 is equal to x, thereby giving us the value of x, performing the division, giving us the value for x to be 8. But then we are not simply being asked the value of x. We were asked to determine the length of RQ and QP, so that we have said that x be the measure of RQ. Therefore, we say that RQ is equal to 8. And QP, which is the inner part of the secant segment, we now subtract 8 from 18 and we arrive at 10. That is actually the measure. PR minus QR will give us QP. Thus, we have here the values or the measures of RQ and QP to be 8 and 10 respectively. There you have it, ladies and gentlemen. Some examples, actually 4 examples, on the application of the tangent secant power theorem, applying that whenever there is a tangent and a secant intersecting outside the circle, we take the measure of the tangent, we square that, we equate that to the product of the measure of the outer segment of the secant multiplied by the entire measure of the secant segment. Again, if you learned something from this video, don't forget to like and subscribe. See you in the next video.